So, good morning, everybody. I'm Thomas Gogel. I'm from Airbus, and to underline it again, what Christian said, no, I'm not from the FAA, and I'm not George. He's sitting over there. Also, for this specific session, which deals with emerging technologies and their link to training, this is not the only presentation. In that context, I'm followed by Francesco Parisi after my presentation from Leonardo. Now, let me handle the man-machine interface first. Here we go. As for the content of the presentations, I will try to give you a bridge from the logic of the EASA safety roadmap into the end, into the technologies that I will be presenting, and how that will relate to documentary issues, how we should document and train then in the end the subjects for the pilots predominantly to handle those technologies. Well, for the big picture, I'm referring back to a topic that Bruce had, which is actually the nice world of fixed-wing aircraft or airline operations, which basically in terms of the safety and accident typology evolution, you can discriminate in three eras. Now, first, I would say, is more or less the barnstorming era, which went into the mid-50s or the 60s, where we had very fragile systems. So actually, when you had an accident, now, yes, quite often it was also human factors, because pilots and flight crews were finding their own ways how to deal with the complex machine. But secondly, also in the technology, it was predominantly dominated to assure the basic safety airworthiness of the contraption that you fly. So it was very much devoted to make flying safe and make the aircraft not break. The second age, which started roughly in the early 70s, was already focused more towards the human and how to make the human better operate the aircraft. It was the first advent of the first races of the glass cockpit, and if you recall the picture that was shown by Bruce, there were the first glass cockpits, as an example, on the A300, S600s, still with traditional instrumentation, but also glass in there, so that much better focus on the humans and how to give them the information actually also enabled a big money savers for the airlines. They got rid of the flight engineer at that time at the equivalent level of safety, so that even pilots, without the higher blessing of an engineer, could by themselves and alone operate the aircraft. So that was basically the outcome of the era. It was also the refocusing a little bit of the technology, not only to prevent aircraft and improve, the airworthiness issues of the technologies, it was also pretty much going into the development of the human-machine interface. Now, talking about ultra-safe systems, which is the emergence of the early 2000s, and to underline it again, what Bruce has said, this holds for the airline industry. We are still at least an order of magnitude of that 1 per million, or I think the airlines are closer to 1 per 5 million flights or cycles, before you have a mishap. So we are at least an order of magnitude of. Still, the same principle for the technology evolution applies, and therefore I pointed out here, we are pretty much focusing now even more on accident prevention technologies. This is what we do in the present age, and that will be basically the focus of this presentation. Also then, to bridge it with the EASA safety roadmap and with the helicopter view on the accidents, I was taking a snapshot out of the annual safety review of the EASA, and I'm just taking arbitrarily one, which was commercial air transport non-offshore. But take any other, take offshore, take non-commercial, it's pretty much the same picture. I highlighted in red those safety issues that you could relate to a technical failure, system reliability or software configuration, or even contained in maintenance. So there are two messages going with this slide. First of all, yes, for sure, that the technical accidents, they are a lower part, but they are not negligible. So we still have to work on those, quite sure. We have to work on those from a manufacturer perspective and from a certification perspective. So yes, we have to improve. But the key message is here, if we want to tackle and reduce the accident rates to a large extent, we better focus on the blue technologies as well. And the blue technologies are highlighted with the red frame, are technologies to avoid operational accidents. So we need technologies to reduce the pilot's workload, to increase situational awareness, and to support decision making. And again, to be said, we are not forgetting the other things, like the further reduction of technical contributors to accident, but also the right-hand side of the bow tie to increase survivability. And I think we have seen quite many issues related to that, like the bird strike resistant window, the crash resistant fuel tanks, and you name it. So now coming what guides us into the technology is a little bit a historical review of what happened. So in former EHAS, now ESPNR, starting roundabout in 2010, multiple hundreds of accidents have been analyzed and categorized, and the 15 most promising, highly promising prevention technologies have been identified in the published reports here, the EASA and the NLR reports. And they have been also recently actually revamped with a publication earlier in this year, with the second round, where we had an assessment actually, you know, what the present status is, and we added a few more technologies. So for the sake of completion, not going into detail, on the left-hand side you see the 15 most promising technologies out of the first report and the additions in the right-hand column. So in the further conduct of my presentation, I will be actually more addressing those that are labeled in green. So those are basically the technologies that enhance situational awareness for the low flyers, obstacle awareness, terrain awareness, and other such subjects. Before bridging over to that, two other technologies that really help getting the pilot, well, either to stay out of trouble or to get out of trouble. And the first one was the before mentioned panic button by Bruce, which should be a feature of any modern autopilot installed in a helicopter or fixed-wing aircraft, general aviation, where you find them quite often. I'm referring to the button which is labeled number 4 on the collective grip. I take the example of an H145 with helionics and the associated autopilot equipment. Quite easily said, you know, if you're getting to your limits, if you're losing control of the aircraft, no, double-click the push button 4, and it engages the autopilot immediately in the airspeed mode and the altitude hold mode and in the heading hold mode. And well, a video actually tells you more than 1,000 words. So we've taken a little video clip, a sequence in the helionics trainer, where you see, first of all, the pilot handling the aircraft, disengaging the autopilot. This is what you see now. He resumes manual flying. And now he stimulates a little bit of loss of control. No? A little bit of a left turn first, putting the nose down. And later in the sequence, you see when it double clicks on the top of the display, you see the illumination of the 3 modes. And then hands off, the aircraft will recover. So it's getting worse, losing control. Now he double clicked the button, has the hands off the controls. And this is what the helicopter does. Now, it levels off, it rolls out, and it maintains an airspeed, it assumes an airspeed of 30 knots. And this is what it does. No? So actually, when you're reaching your limits, as Bruce explained, this is your get out of trouble double push button, which should be in any modern autopilot installed on any aircraft, be it a light aircraft or more complex aircraft. So great feature, addressing one of the big causes of the accidents, which is the loss of control in flight. Next subject I will be presenting to you is actually issues around the vortex ring state. Starting again with things that we have implemented in the autopilot. The autopilot, whenever you have it engaged in any vertical mode in the helionics for autopilot, no? It prevents you from getting into a vortex ring state by itself. So you don't need to think about it. No? So it keeps you basically out of the envelope protected, a yellow area on the bottom part of the graph. So if you're getting slower and you're having a high rate of descent, the helicopter will actually see that it decreases the rate of descent, that you're staying out of that envelope. So under autoflight, the issue is taken care of. Now, as we know, no, helicopter pilots, they like to fly manually. So we were working on a conspicuity and a cue for the pilots in addition to the flight physical cues that quite clearly indicate an impending ring vortex state. But to make it even more obvious, we are working, well, also given on a provided envelope, on a cockpit indication to even make it more obvious to the pilot that he is approaching or in a vortex ring state. And in the end, your man-machine interface has to be as easy as it could be. We heard that before, and it was also quite often stressed by Tony. So when we are approaching a vortex ring in those flight test trials, then basically in the middle of the PFD, you see a caution appearing, a yellow caution that tells you vortex, and you get also an oral alert associated with it. Actually, if you're entering the vortex, and it gets a bit more present warning, so you get a flashing red vortex in the middle of the PFD, and the associated oral warning. So how does that flow down in the proposed training scenario of Airbus? I mean, with all that obviousness of an approaching ring vortex state, with the flight physical cues that you get anyhow, plus potentially such an indication, we again underline our training concept, which is actually recognize in the void, so to train to avoid to get into a vortex, rather than to establish a full ring vortex during the training flight, which we consider more risky training scenario, which should also be avoided by the safety roadmap of EASA. So avoid the ring vortex rather than getting out of it. That should be the focus of the training. This is the message here. Now, as promised before, I would like to present technologies that are actually tackling those 6 subjects that I mentioned before from the top 15 safety-enhancing technologies, which is basically devoted to terrain and obstacle awareness and avoidance. Where we are at now, pretty much state-of-the-art since a few years, is the synthetic vision system. Again, I took the example, stay consistent, for a H145 cockpit, where you have the synthetic vision system either displayed on the primary flight display, where you get a very nice, very obvious, and a very easy to understand 3-dimensional depiction of actually where the mountains, the hills, and potentially the obstacles that you have in the database, where they are. And the plan view on the multifunction display that also with a relative coded, according to the height, relative coded color display, where you immediately see where the trouble areas are from you with the mountains that are higher than you, and where the safe area is where you can fly. So this is a very intuitive system, again, severely helping the pilot. And there's another video clip when you approach actually an obstacle, which is a little tower that you see in the middle of the screen. It's a snippet taken from an actual test flight. We should hear the audio.
Caution. Obstacle.
So there is the obstacle caution.
Warten, bis der Warning sagt.
Warning.
And you're getting
Obstacle.
closer and you get the pull up with the warning. Huh? So all of that is obstacle warning, it's terrain warning.
Obstacle.
Okay.
So it goes pretty much
Warning.
also in the
Obstacle.
direction of HTOS, and the underlying training concept of HTOS will be elaborated by Francesco
Obstacle.
afterwards. So I will continue to drill a little bit more into the technologies, because it does not stop here. There are certain disadvantages associated with the great feature of a synthetic vision system, no? Because again, among us, it's a little bit more a fixed wing system. No? So you have the big obstacles and the big towers. You get an update every 28 days, so you don't have the temporary ones. You might have, at times, inaccuracies in the database. So yes, it's great, but it's not perfect. What actually do we, as low-flying industry, the helicopter industry, need to make it even more safer? We need to see temporary and smaller obstacles. So I think it's not avoidable that we also concentrate on active detection technologies. And we are doing some test trials on our helicopters, where I would like to run you through here quickly. So this is more a plug-and-play subject that we have put on the nose of a 145, where you can actually try out multiple sensors, which is an enhanced vision system, which blends 2 pictures, a visual spectrum and an infrared spectrum to be displayed in the cockpit then. A spherosense or a LiDAR scanner in front of the helicopters. We can also introduce a shortwave radar sensors and blend the pictures. So actually you have multiple ways of sensing that you're processing in a computer together for really concise information. And then the big art is actually how to display it, to make it intuitive and very helpful for the pilot. We heard that before. That is really big art in a more complex system. Actually, to give you an example, what you might see, it's a combination of screen displays, MFDs and PFDs, where we overlay the picture as they come either from the EVS or from the LiDAR or from the radar. And we are also trying out how we could combine that with a helmet-mounted indication. And I actually now would like to focus a bit on the helmet-mounted indication, which is on the left-hand side of the slide. Because here you see, first of all, there's the 2D flight symbology superimposed. So even eyes out, you can see it, and we all know that from the military application. This is extremely helpful and reduces the workload of the pilot. He has an immediate recollection of the flight attitude and the basic flight parameters by just in front of his eyes. But also here on that picture on the left-hand side, you see the huge difference between the normal visual system, which you basically see, which is the gray soup around the top, and down on the right-hand side of the picture. This is actually what you see with the pilot's eyes out of the cockpit. And the squarish thing on the lower left-hand side is the superimposed picture out of the EVS system, where you can clearly discern trees and little hills and roads, which you can't on the other picture. So even that first step of the technology, in my way, is a big way forward and a large improvement of safety, of terrain and obstacle awareness that you can do. Does it stop here? No, not really. Now we are going away from practical flight demonstration still of what we are brewing together right now in the laboratory. And it's artificial intelligence related. No? So it's a bit a hype. No? Even if you buy a lawnmower these days, you get, it's a great artificial intelligence supported thing. No? So we are going down a little bit the same way. It's not a lawnmower, so don't worry. No? So actually you have any sort of a video input, whatever it might be, visual spectrum, and I have a little example of that afterwards, or again, a blended spectrum of whatever. No? Then you process that with, again, a computer, which is for the time being still a little bit on the high end and high priced. No? So we are coming back to the analogy with the human brain. It's not a human brain, but we see that technology coming down in costs tremendously over the past 2 years, as you know. No? So that processes that, and actually you can train, or the algorithm can train itself to recognize patterns. It can recognize masts and chimneys and antennas. It can recognize helicopters, cars, ships, or whatever. You can train it to them. And with that learned database, you can embed that in a flying helicopter. And then in real time, the thing analyzes the picture and gives you a cue where an obstacle is, or a target is, and what it is, and what threat it poses actually. How does it look like in reality? The video source here was obviously infrared. No? So the algorithm can discern by itself whether it's a ship or a little boat. No? It can clearly identify pylons or low voltage power lines or whatever, chimneys with or without smoke. From any angle, it can discern it. Even if it's hard to catch for the pilot's eye, no? Because it's in front of a tree line, like in the picture below, it can clearly point you out there is an antenna or there is a hovering helicopter. So in real time, this can be provided by artificial intelligence. It even goes that a little bit more. So you start the video. So these are two high voltage pylons in the approach area to Donauwörth. So if you start the video, we actually see that it's not really running. Can you click on the video? So by the optical information, the algorithm can determine the distance to the pylons. You see the real distance on the left-hand side as calculated by GPS, and the predicted distance to the right-hand side. So there's a difference on the left-hand pylon of 1 meter in accuracy and a difference of 6 meters in accuracy just from the optical detection to the real value on the right-hand pylon. So I think impressive ways ahead. Well, not really certified yet, as we know, no? Looking on EASA, no? But we are working on it. But does it stop there? No, not really. No? So there are other targets that we have to take care of. Namely, are the aircraft, birds, or UAV, the famous drones. No? So that's, again, it's not a laboratory trial, it's in the free wildlife. You see a flock of birds flying. And you see even birds on the right-hand picture that are moving a little bit and sitting in the trees. So that artificial intelligence algorithm paired with a high-resolution camera can do something that is impossible to the human eye and point it out to it. No? It can use that little targets here. And actually, the algorithm starts working on 4 or 5 moving pixels on the screen. It starts thinking his way and try to identify them. Again, a little illustration. If you start a video, that is the algorithm tracking a drone. Now, it clearly tracks the drone, it disappears. Now, then obviously the algorithm, he learned to know some ducks on the lake by first name. The drone reappears. And then a few seconds later, you always see that there are 2 birds, non-cooperative traffic, flying out of the trees and leaving the picture. So the yellow one is still a drone, flying around left to right. I would say not visible to a human eye, too far away from it, and here come the birds, and they disappear. So this is what we can potentially do for you in the future with the help of artificial intelligence and pointing out non-cooperative traffic and targets on the ground. Long way to go, but we are eyeing that. No? And I think with a pull together, we have to make that emerge, because I think those sort of technologies will lead to a big contribution and leap in safety. Now, how does that bridge into documentation and training, to change the subject a little bit? This looks like a dense slide, but it isn't, but it's one of my favorite slides, I have to say. Well, I'm a ham-fisted fixed-wing pilot, so I'm again taking an example from general aviation, the evolution of cockpits. No? On the upper left-hand side, you see a picture out of the mid-60s of an instrument distribution, which I call the shotgun or shrapnel distribution. No? So whichever engineers got first to the cockpit, he installed whatever he had in the middle of the field of view of the pilot. Whoever came later just then took the sequence. No? It's a Cessna, but it's not typical Cessna. They were all the same. Take the Pipers, I was flying Dorniers, no? That was the shrapnel distribution. And you climb into the aircraft, it was always a little bit like an Easter egg hunt to find your relevant instruments. Still great aircraft, no? I love them. But then came the time, and that reflects a little bit into the second era that I've pointed out before. That was the age for the pilots, no? There was a standardization, there was a normalization of the man-machine interface. You got your standard T indication for the flight instruments. You got a very nice navigational block and system and engine block. They were all very nicely clustered. There was almost no way to confuse any modes. No? You were turning this knob and that got to that instrument. It was very easy. You can jump from one aircraft to the other, from one avionics manufacturer to the other. It still was very intuitive to fly. I would say, for me, as an old guy, those were the golden ages. No? Then the electronic age started. No? It still stays very obvious, and the man-machine interface for each individual subject is very easy to grasp, but you have hundreds and thousands of informations and menu pages and things that you can do, which really requires a lot of training and recency for the pilot in order to be able to fully handle the capability of those complex avionics systems. And it's a little bit, just to make the comparison, like the old cord phone, which was very easy to use for single purpose, for voice communication between human beings, and the smartphone. So who in the room claims that he knows 100% of the function of his smartphone? Nobody, me included. No? If I change my smartphone first time, it's even hard to make a phone call. I have to admit that. No? So it's a training matter, and it's a matter on how to explain it to the flight crew. And it's also for the pilots an urgency to stay on top of that. If you are a frequent VFR flyer that eventually has an IFR flight to do because he must, because of bad weather, every second or third month, you better stay on top of your system. And this is also what Bruce pointed out. So documentation means how, as an enabler to do so, is basically the flight crew operation manual, to name one example. No? So that was developed together Haley Offshore operators and Airbus for the 225 initially, and it is flowing down and in the offshore community via various types. Again, it comes from the more advanced in time airline industry where the FCOMs are around for decades already. No? What does it do? It brings order into chaos. No? It makes a sequential procedural order in how to use the technologies and the cockpit and the automation. This is what it does. No? It gives the human brain, the human mind, an orderly way that you can train how to use it in the cockpit, clearly documented in this document, in the FCOM. We have derived another subject out of that at Airbus, which we call the flight operations briefing load, which I would say is a FCOM Lite, which basically does the same thing. It's not really mission specific, but the depicted example is the FOBN for the auto-flight system for the H-145. It explains intuitive and sequential and procedural, you know, with fingers and hands and pointers and marks in the documentation, what you have to do and how to handle the auto-flight system best. We have done that for various systems and quite a broad range of the Airbus products, and those things are readily available, web-based to be withdrawn. And they are thought for the operators, you know, to help them design their own trainings, to set up their own operational procedures. They are also thought for the pilots for light bedtime reading. It's much better than the flight manual, which it does not replace, to say that explicitly. No? But to stay on top of your system with a lighter manual, which is more intuitive, I highly recommend you the use of the FOBN for the associated type. Last but not least, switching to a training tool, where I've also taken the snippet, the little video sequence for the panic button before that was created with the HATS, the Helionics Advanced Tool Simulator, which is a basic tool that contains Helionics in its core, our new avionics system, which is predominantly thought for crew training, but also for maintenance training. But because it's the real thing, you can also use it for troubleshooting. And now it goes along with the message of Bruce. For the time being, that simulation device, as it looks like with the screens, and by the way, there's an embedded flight loop with X-Plane, not to forget to mention that. That training tool doesn't give you any credit, but who cares? It helps the pilots to stay on top and recurrent on a complex system. And this is very much also as the iOS GNS 750 training app that Bruce has mentioned. It doesn't give you any credit. Who cares? Use it, because it helps you to stay current on your system. And if you have to do this eventual one IFR flight every 2 or 3 or 4 months, this might help you out of trouble. No? Because just try to program a waypoint after 2 or 3 months after you have not done it on one of these systems. It will get to you. If you're in a high workload situation, such a training device is worth its weight in gold. Conclusion of my presentation. Well, at Airbus Helicopters, and you have seen it, we are following strictly and supporting very strictly the EASA roadmap. We think that is the right thing to do for the industry. There is a strong evolution of technologies already available, but I've also indicated to you where we could go in the future with technologies that really help our industry, specifically those mission profiles with the low flyers. And I also pointed out ways of documentation and training means of the over and above that will help you, the operators and the pilots, to tackle the ever-increasing complexity and mightyfulness of the system. Well, in order to move forward on that track, actually, we all need to pull together. No? So it's not a hobby game that Airbus and the other manufacturers are looking very deeply on new technologies. No? And it's not cheap to develop them, to be quite honest. No? But it must be embraced by the operators with the means that they have for sure. And it must be fully supported by the certification and the authorities, so that we get them placed into our industry as quickly as possible. So thank you for your attention.
Hello, I'm Nigel Talbot and I'm an experimental test pilot with Leonardo helicopters. So, let's start with a few basics about helicopter handling qualities. Helicopters fall into three broad categories: unstabilized, those with some kind of basic stabilization system, and automated helicopters. With each step brings an increasing level of capability and safety. Unstabilized helicopters, which cover the majority of small helicopters in service today, require continuous pilot control inputs based on good visual cues to maintain stabilized flight. With an unstabilized helicopter, the pilot is the stability. Flying in bad visual cue conditions, such as night in remote areas, cloud, or poor visibility, can be extremely demanding of pilot skill and leads to a high probability of disorientation and accidents, as the statistics show. A stabilization system helps and makes a helicopter equivalent to the minimum standard required for fixed-wing aircraft. But you still need good skill, training, and experience to fly safely in poor conditions. But, and there is always a but, and it is vital that the pilot fully understands how the basic stabilization system and the automation works and what it can be expected to do in the various operational situations that can occur. Even with helicopters equipped with automation, a high level of attention is needed by the crew to ensure correct use of the system and maintain mode awareness. We need to ensure appropriate cross-check parameters on integrated instruments when using flight directors and autopilots. Flight crews can lose mode awareness or may not understand the interaction between a mode of automation and a particular phase of flight or pilot input.
Rotor low. Rotor low.
Unusual attitudes can still occur due to incorrect use of automation. Fortunately, this time the recovery performed by the pilot was just in time. The accident has been avoided and the consequences have been limited to exceedances of aircraft limitations. Many accidents are related to problems of human-automation interaction, so be aware of the automation weaknesses to make best use of it. And remember, if you fly unstabilized helicopters, be very careful about the conditions you choose to fly in.
Thank you very much. Good morning. I'm Francesco Parisi. I'm an instructor of Leonardo Helicopter Division Training Academy. This video has been prepared by Leonardo on behalf of ESPNR according to the safety promotion program. In this video, narrated by an expert pilot, we review the training steps and some significant phases of flight, faced by an expert general aviation pilot. The video highlighted the importance of training, which allowed the pilot to learn the characteristics and limitations of the onboard automated system, which, if not properly understood, can reduce effectiveness and could affect the safety of the flight. In this example, the pilot, as you see, forgot to apply power while he was climbing using the vertical speed mode on a 3-axis helicopter. In the video, the pilot was distracted during the ground course explanation of the FCS. This, along with an initial confusion generated by unexpected event, in this case a worsening of weather condition, caused an undesired aircraft state, albeit in this case with a positive outcome. In this case, the consequences were limited only to exceedance of aircraft limitation, following to recover the unusual altitude position. Modern helicopters, especially the heavy one, are in most cases equipped with the 4-axis FCS. It is important that pilot training includes detailed explanation of the characteristics and correct use of the equipment available on board. If we consider the glass cockpit layout of modern helicopters, we need to train pilots to understand the man-machine interface, as shown before by Bruce and also by Thomas. We need to know from where information is available, PFD, MFDs. In this case, you see in the below is reported the one possibility about what is able to display the multifunction display. But not only, because together with this, it's possible to display the TCAS information, the maps, SVS, synthetic vision, etc. We need also to know which type of protection are available by a 3 or 4-axis IFCS. In fact, you know that the aim of the IFCS is to protect the envelope of the helicopter, to avoid exceedances. Additionally, we need to build up a new way to cross-check flight parameters in order to monitor the performance of the flight director, of the automation in this case, and select also the appropriate representation of the information available. Together with the situational awareness, we need to develop a flight director mode awareness in order to increase the situational awareness. We need to include in our scan the flight director mode annunciator in order to continuously maintain the awareness of which mode in this moment is engaged. If we see, we had several case studies which the pilot lose the mode awareness and they lose the control of the helicopter. This also helps to avoid the blind spot of our eyes. Because if we do not focus the attention only on one portion of the screen, but we make divided attention, we move our eyes along the screen, we can avoid to lose important information. Among fixed-wing air carriers and some helicopter operators, the management of automation is covered during the type rating ground course and is included in the standard operating procedures, SOPs, and also in the FCOM. In Leonardo, since 2015, we have developed a dedicated course called GLAM, glass cockpit and automation management. In this course, human factor element, complacency, situational awareness, workload management are put in relation with the automation. An overview on how automation can influence the pilot performance is also highlighted. We talk again during this course about the divided attention. We talk about the need to develop a strategy on how to manage the information available. The aim of this course is to allow trainees to achieve a broad perspective of the design philosophy and how to operate the advanced avionics and automation that are featured through the so-called glass cockpit helicopters. A basic knowledge of the system and to improve the effectiveness of the type rating and conversion courses, a broader understanding of how to take best advantage of the automation, and with regard to manufacturer design philosophy and operators SOP. This course is especially recommended for pilots with no experience on glass cockpit helicopters, because our experience showed that many pilots did not have specific training on how to use and how to monitor the performance of the FCS. This is for the automation. Let's see now another topic that needs to be addressed, the controlled flight into terrain. Certain helicopter operations involve greater exposure to risk. In fact, from statistics, we know that most accidents happen during this operation, and the primary cause of these accidents is the CFIT, controlled flight into terrain. This happens because of loss of situational awareness, inadvertent entry in IMC, poor flight planning, weather, fuel management, performance calculation, etc., fixed obstacles, both in vertical and horizontal, power lines, wind farms, wires, etc., mobile obstacle, drones, wingsuit, other aircraft, etc. Controlled flight into terrain continues to be a major category of helicopter accident worldwide with poor survivability characteristics. The primary cause of CFIT accident is a degradation of situational awareness. As shown before by Thomas, to face this course, the industry has developed and is still developing technology that can help pilots to enhance situational awareness and thus increase the safety of the flight. So nowadays we have a helicopter equipped not only with a 3 or 4 axis FCS, we also have HTAVs, TCAS, digital map, synthetic vision, enhanced visual system, LiDAR, etc. One specific technology that aims to increase the situational awareness is the HTAVs. Put simply, this system warns pilot when the helicopter is too close to the ground, you know. We saw that from the introduction of TAVs in the 70s, the number of CFIT accidents has been reduced significantly. The TAVs warning is normally the flight crew's last opportunity to avoid CFIT. If we do not follow, especially we do not have a visual reference, then the information provided by the CFIT, we can have a problem. But also this system needs to be known because, you know, all system needs to be known in terms of how the system is designed, how it works, limitation. Typically, the theoretical knowledge of this system, and together with other systems, is provided during the type rating ground courses. Proper pilot training on CFIT awareness is equally important to reduce the CFIT risk. Most of the factors that have been identified are the result of deficiency in flight crew training program. I have a personal experience that when I train, in some cases, in the simulator during the IFR flight, despite there are advice, alert from the CFIT, the pilot do not react, even that they do not have any visual reference. Therefore, training becomes a significant factor that contributes to CFIT. Flight crew needs to be properly trained and disciplined because technologies, NAVAIDS, SOP, normal procedure will not prevent CFIT. Theoretical knowledge should not be enough. We need to train pilots on how to use this system with, for example, dedicated simulator sessions where the use of HTAVs together with the soft and protection provided by the FCS are tested in a safe environment. Also for this course, Leonardo has an available course that is called CFIT, Helicopter CFIT Education Program, where together with the theoretical elements that includes the threat and error management, risk management, case study, presentation on how the different technology, for example, the LIDAR, the SVS, the enhanced visual system are explained in the classroom. Together with this theoretical knowledge, there is also a practical training that is conducted in the simulator. This training includes also not only the use of the different part of the CFIT, but include also what we have to do in case of inadvertent IMC, the escape in case of brownout, whiteout, in order to train the pilot to increase the situational awareness to react promptly to what happened in the helicopter. So, conclusion. As shown before by Thomas and followed by the update, recent update, in 2014 he has conducted a study developed by NLR where some new available technologies are reported. This study consists in listing technologies and link them with the accident causes and contributing factors as identified by the in EASA analysis, and then to assess the potential of these technologies to mitigate safety issues. Whereas technology, experience, safety operation, and training all introduce barriers, their combined use appears much more effective when it comes to increase flight safety. So, technology can help to reduce the number of accidents, but we must, in parallel, develop appropriate training. Otherwise, the technology alone is not sufficient. Thank you very much.